Imagine for a moment that you stand on the cusp of a new day. The horizon begins to glow, not with the familiar promise of a singular dawn, but with a soft bifurcated light, a celestial schism. To your left, a colossal sun of brilliant molten gold ascends, painting the alien clouds in hues of fire and honey. Minutes later, from a different point on the compass, its companion follows. A smaller, fiercer star of incandescent blue-white, it cuts across the sky, casting a second razor-sharp set of shadows that chase the first. This is a world born of two stellar parents, a planet caught in the intricate gravitational waltz of a binary star system. It is a spectacle of unimaginable beauty, a vision that has haunted our science fiction dreams for generations, a sky that feels both profoundly alien and strangely primordially familiar. But beneath this breathtaking celestial panorama lies a question, one of the most tantalizing and formidable in all of science. Could this cosmic masterpiece, this sky with two suns, truly be the backdrop for the greatest masterpiece of all? Could life actually arise, survive, and thrive in such a place? For decades, the answer from the halls of science was a resounding, uncompromising no. The very idea was relegated to the colourful pages of fantasy, a charming but ultimately implausible trope. We saw it etched into our cultural consciousness, the iconic double sunset over the desert plains of Tatooine, a symbol of a galaxy far, far away. It was the perfect visual shorthand for a reality detached from our own, because a world like that, we were told, could never be. The scientific consensus was built on a foundation of brutal cosmic mechanics, a logic that saw binary systems not as potential cradles for life, but as violent, chaotic arenas of gravitational destruction. They were seen as celestial wrecking yards where the raw power of two suns conspired to make the formation and stability of life-bearing planets an almost mathematical impossibility. In our models, any fledgling world trying to coalesce in the protoplanetary disk surrounding two stars was a tragic character in a cosmic drama. It would be bullied, harassed by a relentless gravitational torment. The two stars, locked in their eternal orbit around a common centre of mass, the barycenter create a gravitational field of dizzying complexity. It's not the simple, elegant, predictable gravity well of our own sun, which holds its planets in serenely stable, almost circular paths. Instead, it is a swirling dynamic vortex, a landscape of gravitational hills and valleys that shift and warp with every passing moment. A young planet in such a system would be subject to a constant tug of war. Its orbit would be stretched, then compressed, then twisted. It might be violently ejected from the system, entirely flung into the cold, lonely darkness of interstellar space like a stone from a slingshot. Or in an even more catastrophic fate, its orbit could decay, sending it on a fatal spiral into the fiery embrace of one of its parent stars. These were not mere speculations, they were the stark predictions of physics. There existed in these theoretical models vast zones of instability, entire regions of space, where a stable planetary orbit was simply forbidden by the unforgiving laws of celestial mechanics. The very architecture of a binary system seemed designed to obliterate the calm consistency that we believe life so desperately needs. And even if by some miracle a planet could form and cling to a stable orbit, it would face a second, equally daunting trial by fire. Life as we understand it requires a remarkably steady input of energy. Our Earth basks in the reliable glow of a single middle-aged star, a furnace that has burned with reassuring constancy for billions of years. This stability has allowed life to take hold, to adapt and to flourish. But a planet in a binary system would know no such peace. It would be bathed in the light of two separate stellar engines, and those engines might be radically different from one another. Imagine a world orbiting a placid yellow star much like our own sun, but that star is in turn locked in a dance with a volatile red dwarf. The yellow star provides a gentle, life-sustaining warmth, but the red dwarf is a cosmic firecracker, prone to unpredictable, violent flares that can erupt with the force of 1 billion atomic bombs. These stellar tantrums would unleash torrents of high-energy radiation X-rays and charged particles that would wash over the hapless planet. Such a celestial blowtorch could sterilize a world in an instant, stripping away its atmosphere, boiling its oceans, and scouring its surface of any life that dared to emerge. The very air would be torn from the sky, the water vaporized, leaving behind a barren, irradiated husk. The rhythm of light and heat would be a chaotic symphony. If the planet's orbit were wide, circling both stars as a pair, it would experience a bizarre cycle of double daylight, followed by a brief star-filled night when both suns set together. If the two stars were themselves in a close fast orbit, the planet's sky would see a constant flickering, a pulsing of light as one star periodically eclipsed the other, creating sudden dramatic dips in the energy reaching the surface. Temperatures could swing wildly not over seasons but over days or even hours. How could any organism possibly adapt to such a relentless, unpredictable barrage of energy and radiation? This leads us to the most critical obstacle of all, the very concept that has defined our search for life beyond Earth, the habitable zone. We call it the Goldilocks zone, that narrow, perfect ring around a star where a planet's surface temperature is just right, not too hot, not too cold for liquid water to exist. For a single star like our Sun, this zone is a relatively stable, well-behaved band of cosmic real estate. Earth has resided comfortably within it for its entire history. But for a binary system, the habitable zone is a phantom. It's not a simple ring, but a complex, shimmering, three-dimensional space that contorts and breathes with the orbits of its two parent stars. As the two suns circle each other, moving closer and then farther apart, their combined energy output, as seen from a nearby planet, fluctuates. In response, the habitable zone itself pulses. It expands and contracts it, warps and twists a ghostly ribbon of warmth dancing to the gravitational music of the system. A planet might find itself perfectly situated within this zone for a time, its oceans warm and its climate temperate. But then, as its suns drift apart in their orbits, the zone could shrink, plunging the world into a catastrophic, deep, freezing ice age. Later, as the stars swing back towards each other, their combined heat intensifies, and the zone surges outwards, engulfing the planet in a runaway greenhouse effect, boiling away the very oceans that once nurtured the hope of life. This planet would be on a climatic roller coaster, with no end, locked in an eternal cycle of being frozen, thawed, and then cooked. It was this triple threat, gravitational chaos, radiological assault, and a habitable zone in constant violent flux, that for so long cemented the verdict worlds with two suns were cosmic curiosities, but they were no place to call home. The dream of life under a double sunset was, it seemed, destined to remain nothing more than a beautiful, impossible fiction. And then we looked again. We built new eyes instruments of breathtaking sensitivity and pointed them towards the heavens with a singular purpose to find planets beyond our solar system. The Kepler Space Telescope, a revolutionary planet hunter, began its patient vigil staring unblinkingly at a single patch of sky, monitoring the light of over 150,000 stars. Its method was beautifully simple in concept, yet fiendishly difficult in practice. It watched for the slightest, most minuscule dip in a star's brightness, the telltale sign of a planet passing in front of it a transit. It was a search for shadows, for the ghost of a world crossing its sun. For years, Kepler delivered a bounty of discoveries revealing a galaxy, teeming with planets of all shapes and sizes, most orbiting single stars like our own. The data confirmed our models. The universe was, it seemed, orderly, until it wasn't. In 2011, the Kepler team was analysing the light from a pair of stars catalogued as Kepler-16, located 200 light-years away. These two stars, both smaller and cooler than our Sun, were locked in a tight 41-day orbit around each other. As expected, the scientists saw the light from the system dim regularly, as the two stars eclipsed each other, a clockwork celestial dance. But then they saw something else, something impossible. There were other dimming events, ones that didn't fit the pattern of the stars. They were fainter, more subtle, and they followed a different rhythm. The team ran the calculations again and again, checking for errors, for any other explanation. There was none. The only conclusion that fit the data was as shocking as it was profound. There was a third body in the system. A planet about the size of Saturn was orbiting both stars. It was the first unambiguous discovery of a circumbinary planet, a world with two suns. It was Tatooine made real. The discovery of Kepler-16b sent a shockwave through the astronomical community. Here was a planet existing precisely where our best model said it couldn't. It was orbiting in a stable, predictable path in a system that was supposed to be a chaotic gravitational minefield. The impossible world was in fact there, and it wasn't alone. Soon more were found. Kepler 34b and Kepler 35b, a pair of gas giants, each orbiting a different double star system. Then Kepler 47, a system that shattered expectations even further, boasting not one but multiple planets orbiting its two suns. One of them, Kepler 47c, was even found to be orbiting within that system's shifting, pulsating habitable zone. These were not flukes, they were a fundamental feature of the cosmos. We had been looking at the universe with a profound bias, an unconscious assumption that solar systems should look like our own. The existence of these impossible worlds forced us to throw out the old rulebooks and confront a new, more complex and far more exciting reality. The chaos of binary systems wasn't always a destructive force. Somehow, under the right conditions, this intricate gravitational dance could not only allow for planets, but could shepherd them into existence, nurturing them in stable orbits against all odds. The discovery of these real-world Tatooines didn't answer the question of life. It amplified it, transforming it from a philosophical musing into a tangible scientific quest. The gate was now open. We now stand at the threshold of a new frontier in astrobiology, a paradigm shift in our search for life in the universe. The question is no longer if these worlds can exist, but what they are like, and whether the spark of biology could ignite upon their shores. This is the journey we're about to embark on. We will move beyond the fiction and delve into the intricate science, exploring the real worlds that are challenging our most basic assumptions about what makes a planet habitable. The discovery of circumbinary planets has opened a floodgate of new questions, each more profound than the last. How would life evolve on a world where the primary source of energy is not one but two stars of potentially different colours and temperatures? Photosynthesis on Earth is tuned to the specific light spectrum of our yellow sun. What would a plant look like if it had to evolve to capture energy from both a red dwarf and a blue giant simultaneously? Would its leaves be black to absorb every possible photon? What kind of eyes would an animal evolve if its world had two suns casting two distinct shadows, creating a visual environment of unparalleled complexity and depth? How would circadian rhythms, the fundamental internal clocks of life, develop in a place, without a simple 24-hour cycle of light and dark? And what of the seasons? They would not be governed by a simple axial tilt, but by a bewildering combination of the planet's own orbit and the slow, grand orbit of its two parent stars. A great year in such a system could last for centuries, bringing with it profound long-term shifts in climate, a rhythm of ages to which all life would have to adapt or perish. To answer these questions, we must challenge our deepest Earth-centric biases. Our planet orbiting its solitary stable sun may not be the universal template for life. It may in fact be just one model among many. Perhaps the chaos and variability of a binary system, long thought to be a detriment to life, could in some cases be a catalyst driving evolution in new and unexpected directions, fostering a resilience and adaptability far beyond what we have ever imagined. The universe is not obligated to conform to our expectations. Its capacity for invention is limitless. Our task is now to open our minds and follow the evidence wherever it may lead us. To truly understand the potential for life in these extraordinary systems, we must first grasp the force that dictates every aspect of their existence. It is the invisible hand that sculpted these worlds, the choreographer of their celestial dance, the ultimate arbiter of their fate. It is the fundamental power that holds suns together and keeps planets in their place. Before we can explore the biology, we must first master the physics. We must journey to the heart of this cosmic waltz and confront the awesome, intricate, and surprisingly creative power of gravity. What if our most cherished story of creation, a single benevolent sun warming a solitary world, is not the universe's only tale? What if scattered across the cosmos are worlds bathed in the light of two suns, planets with double dawns and lingering spectral twilights? For much of human history, this was the exclusive domain of science fiction, a fantastical backdrop for stories of distant galaxies. It was an idea so alien, so contrary to the stable, predictable clockwork of our own solar system, that even as we began to hunt for planets beyond our own, We considered these twin star systems to be cosmic dead zones, the great celestial wildernesses where the fundamental laws of nature had posted a clear and unambiguous sign, no worlds allowed. To understand the depth of this conviction, you have to journey back with us back to a time not so long ago, when the very notion of finding any planet outside our solar system was a revolutionary dream. The late 20th century saw the dawn of a new kind of exploration. Instead of ships, we used colossal mirrors. Instead of traversing oceans, we peered across unfathomable gulfs of light years. We were planetary prospectors sifting through the faint rhythmic signals hidden in the light of distant stars. Our methods were born of incredible ingenuity, turning stars themselves into instruments for detection. We looked for the almost imperceptible wobble of a star, the gentle gravitational dance induced by an unseen planetary partner. We searched for the telltale dimming a minuscule repeating eclipse as a world passed between its star and our waiting telescopes. Each new candidate, each potential world, was a testament to our persistence. But this grand search was conducted with a powerful unspoken bias. We were looking for reflections of ourselves, for systems that mirrored the architecture of our own cosmic home. The perfect targets were stars like our sun's solitary, stable and predictable. These single points of light offered a clean gravitational canvas, a place where planets could form and settle into the same kind of orderly, long-lived orbits that grace our own solar system. And in the star catalogues, these lonely suns were vastly outnumbered. For when we gaze out into the Milky Way, we find that the universe has a profound preference for companionship. More than half of all the stars you see, and perhaps as many as 85% of the most massive ones, are not alone. They are bound together by gravity and breathtaking partnerships, pairs and trios of stars locked in an eternal waltz. They are binary systems, and to the first generation of planet hunters they represented not an opportunity but a problem, a profound and seemingly insurmountable mathematical nightmare. The skepticism was not born of a failure of imagination, but from a deep respect for the raw, untamable power of gravity. In our solar system, the sun is the undisputed sovereign. Its gravitational authority is absolute, dictating the paths of every planet, asteroid and comet with unwavering precision. It is a simple, elegant monarchy. A binary star system, however, is a gravitational duel. It is a kingdom ruled by two feuding monarchs, each constantly vying for influence their overlapping gravitational fields, creating a complex shifting landscape of unseen forces. For any planet attempting to survive in such a domain, life would be a perpetual state of gravitational chaos. This was the fundamental hurdle, the great filter that astronomers believed would mercilessly cull any chance for planetary existence in these systems. The very process of creation, the delicate miracle that transforms a disk of dust and gas into a cohesive world, seemed utterly impossible amidst such turmoil. Think of how a planet is born. Around a young single star, a vast spinning platter of primordial material settles into a relatively flat orderly disk, a protoplanetary disk. Within this cosmic potter's wheel, tiny dust grains begin to stick together. Electrostatic forces like the static cling in your clothes draw them into larger and larger clumps. Gravity then takes over, pulling these pebble-sized bodies into kilometre-wide planetesimals, the building blocks of planets. It's a slow, patient process of accumulation unfolding over millions of years within a relatively stable, protected environment. Now introduce a second star into this delicate nursery. The cosmic potter's wheel is violently shaken. The companion star, even from a distance, acts as a titanic gravitational egg beater, its influence churning and disrupting the fragile disk. Its gravity raises immense tides within the gas, creating powerful spiral waves that sweep through the material. It doesn't just stir the disk, it can twist it, warp it, and even tilt it at a severe angle, a phenomenon known as disk precession, turning the entire planet-forming plane into a wobbling, unstable gyroscope. Material that might have gently coalesced is instead flung into chaotic trajectories. Some of it is hurled violently outward, ejected from the system entirely to become a lonely orphan in the interstellar void. Other material is shepherded inward on a collision course to be devoured by one of the stellar furnaces. The safe zones for planet formation, the calm eddies where worlds might grow, shrink dramatically or vanish altogether. The system becomes a celestial demolition derby, where the chances of constructive accretion are overwhelmed by the forces of gravitational disruption. For early theorists, the models were brutal and clear. The constant gravitational interference from a stellar sibling would effectively starve a protoplanetary disk, preventing the birth of anything larger than an asteroid. The cradle of creation was being perpetually robbed, but even if by some miracle a planet could manage to form against these overwhelming odds, its struggle for survival had only just begun. It now faced a lifetime of navigating the most treacherous orbital pathways in the cosmos. In a single-star system, a planet's orbit is a simple closed ellipse, a predictable path it can trace for billions of years. This stability is the essential prerequisite for life. It ensures a consistent supply of energy, preventing the planet from freezing in the abyss or boiling under a sudden catastrophic approach to its sun. In a binary system, this beautiful predictability is shattered. The planet is no longer beholden to one master but two. It is subject to the infamous three-body problem, a mathematical puzzle so complex it has no general exact solution. The planet's path is no longer a simple ellipse but a maddeningly complex, ever-changing trajectory, constantly being perturbed by the shifting positions of the two stars. Every orbit is a high-wire act without a net. The companion star's gravity can pull the planet's orbit into a more elongated, eccentric shape. A world that once enjoyed a temperate circular path might suddenly find itself thrown onto a wild, comet-like trajectory, swinging in for a scorching pass by one star before being flung out into the frigid depths of its system. Seasons as we know them would cease to exist, replaced by erratic, violent swings between fire and ice. The dangers were more profound than just climatic catastrophe. These gravitational nudges accumulating over thousands or millions of years could lead to one of two grim fates. The planet could be destabilized entirely, its orbit becoming so chaotic that it is eventually ejected from the system, with tremendous force, a rogue world condemned to wander the cold, dark emptiness between the stars forever. Or its orbit could decay inward, spiraling it towards a fiery demise as it's consumed by one of its two suns. For scientists running the first computer simulations of these systems, the results were a graveyard of digital worlds. Planets were tossed out, swallowed or shattered in collisions. Stable long-term orbits seemed to be the rarest of exceptions, mathematical flukes that could not be relied upon to exist in nature. The verdict seemed written in the language of physics itself. Binary star systems were simply too violent, too unpredictable, too fundamentally hostile to harbour worlds. They were cosmic blenders, not planetary nurseries, and so for years the vast majority of stars in our galaxy were placed on the Do Not Observe list for planet hunters. It was a pragmatic decision, a focusing of limited resources on the targets deemed most likely to yield a discovery. Why search for planets in a place where all our knowledge suggested they couldn't possibly survive? Yet as our understanding of gravity and celestial mechanics deepened, the picture began to gain some nuance. The universe is rarely so black and white. Theorists began to realize that the chaos of a binary system was not uniform. The fate of a potential planet depended entirely on its location, on where it dared to place its orbit within this complex gravitational landscape. Two fundamental arrangements began to emerge from the models, two possible configurations that might offer a haven of stability amidst the storm. The first and most intuitive distinction was the distance between the two stars themselves. Not all binary systems are created equal. Some are known as close binaries, where the two stars are locked in a tight, intimate embrace. They may orbit each other in a matter of days or even hours, their stellar atmospheres sometimes touching and sharing material. In such a system, the two stars behave almost as a single gravitational object, their individual fields merging into one complex, rapidly changing behemoth. For a planet, this environment remains almost hopelessly chaotic. But other systems were wide binaries. Here the two stars keep a respectful distance. They might be separated by dozens, hundreds, or even thousands of times the distance between the Earth and our Sun. They are true siblings, bound by gravity, but each reigning over its own substantial sphere of influence. Their orbital dance is a slow, majestic affair taking centuries or millennia to complete. It was in these wide binaries that a glimmer of hope first appeared. This crucial distinction between close and wide binaries gave birth to the two primary models for planetary survival. The first, and what was considered the most plausible scenario, is known as an S-type orbit. The S can be thought of as standing for satellite, or secondary. In this arrangement, the planet orbits just one of the stars, treating it as its primary sun. The second star is a distant but ever-present companion in its sky. For this to work, the planet must be nestled in close to its host star deep within its gravitational well, where its authority is nearly absolute. The companion star must be far enough away that its gravitational influence is reduced to a gentle, manageable perturbation, rather than a system-shattering force. Imagine a child holding tightly to one parent's hand while the other parent stands across a large room. The child is securely bound to the first parent, and while aware of the second, is not in danger of being pulled away. A planet in a stable, S-type orbit experiences a similar security. Its primary star is its anchor, its gravitational centre. The distant stellar sibling might cause minor wobbles in its orbit over eons, perhaps influencing long-term climate cycles, but it does not pose an existential threat. This was the first crack in the wall of skepticism. Perhaps planets couldn't form between two stars, but they could certainly exist around one star. In a binary pair, provided the separation was great enough, suddenly a vast number of star systems were back on the table for planet hunters. The search could expand to include these intriguing systems looking for worlds that experienced the light of their own sun, but also shared their sky with another, a brilliant star-like beacon that would outshine any planet or moon, a world with a sun and a second distant sun. The other possibility was far more radical, far more challenging to our understanding of physics, and far more evocative of the iconic images from science fiction. It is the P-type, or circumbinary orbit. Here the planet does not orbit one star or the other, it orbits both. It is a world of two suns in the most literal sense, tracing a vast majestic path around the common centre of mass of the binary pair. This is the Tatooine orbit. For this to be even remotely possible, the planet must be very far away from the central stars at a distance many times greater than the separation between the two stars themselves. From the planet's perspective, the two suns are so close together in its sky that their combined gravity acts like that of a single, albeit slightly lopsided object. It is orbiting the system's barycenter, the gravitational balance point around which the two stars execute their frantic close-quarters dance. If the S-type orbit is a child clinging to one parent, the circumbinary orbit is a child watching from the far side of the ballroom as its parents spin together in a dizzying waltz. The stability of such an orbit is perched on a knife's edge. Too close, and the complex swirling gravity of the individual stars will tear the orbit apart, ejecting the planet. There exists a critical inner boundary, a zone of instability that no circumbinary planet can cross and survive. The theoretical challenges to forming a planet this far out in a stellar system were immense. The protoplanetary disk would be thinner here, the material more diffuse, and the time required to build a planet exponentially longer. To the sober minds of astrophysicists in the 1990s, the circumbinary planet was a beautiful but highly improbable theoretical curiosity, an elegant solution on paper that nature had likely never bothered to construct. And so, the stage was set. The scientific community, armed with a powerful understanding of gravity, had drawn its battle lines. Planets were the children of single stars. Binary systems, for the most part, were barren. The most you could hope for was a world in a wide S-type orbit, a planet with a distant bright companion. The idea of a world orbiting two suns simultaneously, a true circumbinary planet, remained a fantasy. The theories were elegant, the models were clear, and the conclusion seemed inescapable. Twin suns were cosmic cradles of chaos, not life. They were fascinating objects for stellar physicists, but cosmic disappointments for the burgeoning field of exoplanet science. But the universe has a habit of ignoring our assumptions. It delights in populating the cosmos with objects our theories deem impossible. And out in the darkness, a signal was beginning to pulse a faint heartbeat from a world that by all rights should not exist. A world that would force us to redraw our maps of the cosmos and reconsider what it truly means to be a planet. The first evidence was about to arrive, not from a search around a sun-like star, but from the unlikeliest of places, the ticking heart of a dead one. and so the verdict delivered by the cold, unforgiving laws of gravity seemed absolute. The cosmic cradles surrounding twin suns were thought to be zones of utter chaos, violent arenas where the gravitational crossfire of two stars would obliterate any chance for worlds to form. Early computer models, our first digital windows into these systems, painted a grim and consistent picture. Protoplanetary disks, the delicate nurseries of creation, were not nurtured here. Instead, they were shredded, their dust and gas flung into the void by a relentless gravitational whipsaw. For decades, this was not mere theory. It was the prevailing wisdom, a foundational assumption that placed a stark, keep-out sign across nearly half the star systems in our galaxy. The argument was elegant in its brutal simplicity. How could something as fragile as a planet coalesce from a swirling cloud of debris while being constantly pulled in two different directions? It would be like trying to build a sandcastle in the middle of a hurricane. The search for such planets therefore was seen by many as a fool's errand, a quest for something that celestial mechanics had already forbidden. Early telescopic surveys seemed to confirm this bleak assessment, returning again and again with nothing. Silence from the systems with two suns. A profound, echoing emptiness that solidified skepticism into scientific dogma. The universe, it seemed, had drawn a line. Planets could have one parent star, and that was that. But science is a story of overturned dogma of nature, revealing a complexity that mocks our simple assumptions. And in 2009, humanity launched an instrument that would become the ultimate arbiter in this silent cosmic debate. It was not designed with the specific goal of challenging this particular piece of wisdom, yet it was perfectly engineered to do so. This was the Kepler Space Telescope, an unblinking eye sent to stare with unprecedented patience and precision at a single patch of the Milky Way. Its mission was breathtakingly straightforward: to watch for shadows. To measure the light of over 150,000 stars, looking for the faintest, most minuscule dimming that might betray the presence of a planet passing in front of its sun. This is the transit method, a technique of profound subtlety. You're watching for a star's heartbeat to momentarily stutter, for its light to dip by a fraction of a percent, a telltale sign that a world dark and silent is making a celestial passage. For a single star system, this signal is regular, predictable, as reliable as a clock. The dip comes, the dip goes, and with each pass the planet's existence is confirmed, its orbital period measured. It is a clean, beautiful rhythmic signal. But what would the signature of a planet in a binary system even look like? The models that said they couldn't exist also implied that even if they did, their signal would be a chaotic mess, a puzzle of overlapping shadows and irregular timing hopelessly buried in the noise. The expectation was that Kepler in its grand survey would simply reinforce the silence. It would look at the thousands of binary stars in its field of view and find nothing but the intricate pulsating dance of two stars alone. For the first few years the dogma held. Kepler found thousands of candidate planets, a spectacular confirmation of how crowded our galaxy truly is. But they were all orbiting single stars, lonely suns with their own families of worlds. The binary systems remained stubbornly, frustratingly empty, just as the theories predicted. The data miners, the astronomers and astrophysicists sifting through the torrent of information from Kepler saw the complex light curves from these twin star systems and often classified them as confounding variables, as noise to be filtered out. The light from these systems was already a complex symphony, with the two stars eclipsing each other, their brightness swelling and fading in a complicated rhythm. Finding the whisper of a planetary transit within that roar seemed impossible. But then within the data from a system designated Kepler-16, a team of scientists noticed something that defied easy explanation. The primary star was dimming in ways that the orbit of its companion star simply could not account for. There were extra dips in the light, shallow and brief, and they were not random. They possessed a strange complex pattern, a third layer of rhythm woven into the established beat of the two suns. At first it was dismissed, a technical glitch perhaps, or star spots, great magnetic storms on the surface of one of the stars mimicking the shadow of a planet. Every alternative, every more conventional explanation was tested, simulated, and ultimately discarded. None of them fit the data. The numbers on the screen were telling a story that was supposed to be impossible. With mounting excitement and a palpable sense of disbelief, the team began to model a new radical hypothesis. What if the anomaly was not an error? What if it was real? What if a planet was out there, a single world orbiting both stars at once? The moment this third body was introduced into their simulations, the chaotic, inexplicable signal suddenly resolved into perfect, breathtaking clarity. The model was a perfect match. The shallow dips in light occurred when the planet passed in front of the larger, brighter star. The even fainter dips happened when it transited the smaller, dimmer companion. And most remarkably, there were moments when the planet's passage was completely invisible, its shadow falling on one star just as that star was being eclipsed by the other. The complex, messy signal was not noise at all. It was the intricate signature of a world with two suns. It was the discovery of Kepler 16b, a cold Saturn-sized gas giant on a wide 229-day orbit around its twin parents. The announcement sent a seismic shockwave through the astronomical community. Here in the light from stars 245 light-years away was the definitive, unambiguous refutation of decades of scientific certainty. It was a single data point that demolished an entire theoretical edifice. Dubbed Tatooine by a captivated public in honour of the fictional twin-sunned world from science fiction, Kepler 16b was more than just a new planet. It was a revelation. It was the first proof that a cosmic cradle, even one rocked by the gravity of two stars, could indeed give birth to a world. The impossible, it turned out, was merely the unobserved. And once astronomers knew what to look for, once they had the key to deciphering these complex signatures, the floodgates broke open. The discovery of Kepler 16b was not an anomaly. It was the first drop of rain before a deluge. Scientists developed new, more sophisticated algorithms tools designed specifically to hunt for these ghosts in the machine to untangle the interwoven light curves of binary stars. They went back to the mountains of archived Kepler data, the very signals that had once been dismissed as noise, and began to see them with new eyes. What they found was staggering. The silence from the binary systems had been an illusion, a failure of our own perception. They were not empty at all. They were teeming with worlds. One after another, the discoveries poured in. Kepler 34b and Kepler 35b, a pair of gas giants, each orbiting a tight binary pair. Kepler 38b, a Neptune-sized planet whose two suns were of significantly different mass, creating an even more complex gravitational environment. Then came Kepler 47, a system that truly shattered all remaining expectations. It hosted not one but 3 known planets orbiting a pair of stars, a fully fledged planetary system proving that circumbinary worlds were not just solitary outcasts but could form in families. And these were just the circumbinary, or P-type, planets, those that orbit both stars from a distance. Kepler's data also began to unveil a treasure trove of S-type planets, worlds that orbit just one of the two stars in a binary pair living out their existence, with a brilliant distant companion star hanging like a permanent blazing beacon in their skies. Suddenly the galaxy looked profoundly different. The discovery that planets in binary systems were not rare but were in fact common forced a fundamental re-evaluation of where we might find worlds. Nearly half the stars in the Milky Way had been effectively crossed off the list of potential homes for planets. Now, in a breathtaking reversal, they were all back on the map, doubling the number of potential cosmic cradles in an instant. This new census of worlds revealed a gallery of celestial objects more strange and diverse than we had ever imagined. We found planets on wildly eccentric elliptical orbits careening through their systems like gravitational slingshots, experiencing dramatic swings in temperature as they were flung from blistering proximity to their twin suns out into the frigid depths of their system. We found worlds locked in precarious orbital resonances, their stability, a delicate balancing act on a gravitational knife's edge where the slightest nudge could send them spiraling into one of their stars, or eject them from the system entirely. We detected gas giants huddled so close to their stellar parents that their atmospheres were being boiled away by a double dose of stellar radiation, great plumes of hydrogen bleeding into space under the assault of 2 celestial blowtorches. Imagine standing on the surface of a moon, orbiting one of these worlds. Your sky would not be ruled by a single predictable sun. It would be a stage for a perpetual silent ballet of light and shadow. You would witness two sunrises and two sunsets, perhaps of different colours, one a brilliant yellow-white, the other a fiery orange-red. At times, the two suns might rise together, casting double shadows that stretch and dance across the landscape. At other times, one might rise as the other sets, bathing the world in a continuous perpetual twilight. Seasons on such a world would be governed not merely by the tilt of its axis, but by the slow gravitational waltz of its two parent stars. There would be stellar seasons, long periods where the stars draw closer together in their own orbit, bathing the planet in extra warmth, followed by epochs where they drift apart, plunging the world into a deeper chill. The very concept of a day, or a year, would become a far more complex calculation, a rhythm set by three celestial bodies, not two. These were not just statistical data points. They were portraits of alien environments so fundamentally different from our own that they challenged the very limits of our imagination. The existence of this diverse planetary zoo presented astronomers with a profound and exhilarating crisis. Their models of planet formation, which had worked so well for single-star systems like our own, were completely and utterly broken. The core accretion model, our standard picture of how planets are built, relies on stability. It requires a calm, orderly protoplanetary disk where tiny dust grains can gently stick together, growing into pebbles, then planetesimals, then planetary embryos over millions of years. This process is delicate. It needs a stable gravitational anchor, a single central star, to orchestrate the construction. But in a binary system, there is no single anchor. There is a gravitational maelstrom. The tidal forces from a companion star should by all rights create spiral waves that tear through the disk, increasing the collision speeds of particles to the point where they shatter on impact rather than stick together. The companion star should act like a giant gravitational egg beater, stirring the mixture so violently that no planetary lumps can ever form. Furthermore, the chaotic resonances, the zones of gravitational instability, should act as cosmic bulldozers, clearing out vast swathes of the disk and starving any potential protoplanets of the raw material they need to grow. The planets Kepler found simply should not be there. They were standing in places our theories had declared forbidden zones. The confrontation was no longer theoretical, it was observational. Reality was showing us a universe far more creative and resilient than our simulations had allowed. The neat, tidy textbooks on planetary formation were suddenly obsolete. The fundamental question had shifted from if these planets could exist to the far more difficult and exciting question of how. This forced scientists back to the drawing board, compelling them to rethink the very mechanics of these cosmic cradles from the ground up. If planets were indeed forming in these violent environments, then the protoplanetary disks themselves must be far more robust and long-lived than previously believed. Perhaps the gravitational stirring in some cases isn't purely destructive. Could it concentrate material in specific gravitationally stable pockets, so-called safe havens, where the chaotic forces cancel each other out, allowing planetesimals to grow in relative peace? Another tantalizing possibility involves planetary migration. Perhaps these worlds are not born in the chaotic inner regions where we find them. They might form much further out in the disk, far from the gravitational turmoil of the central stars in a region of relative calm. Then over millions of years they could slowly, carefully migrate inwards, their orbits shepherded by the gravitational influence of the remaining disk material, until they settle into the stable, if sometimes eccentric orbits we observe today. This would mean that the planet itself is a survivor, a world that ran a perilous gravitational gauntlet and somehow emerged intact. Each new circumbinary planet discovered is a clue in this grand detective story, its mass, its orbit, and its composition providing a forensic snapshot of its violent birth. We are now in a new era of exploration armed with the knowledge that these systems are not barren. They are laboratories. They are extreme test cases that push our theories of creation to their absolute limits. And as we stare into the light of these twin suns, we are forced to confront an even more profound possibility. If worlds can form in such tumultuous conditions, surviving and even thriving in a reality of two suns, then what other marvels has the universe hidden from us, waiting just beyond the edge of our imagination? So, a planet can survive the gravitational brawl of a binary system. We have seen the equations balance the orbits settle, into patterns of unexpected grace, proving that celestial mechanics does not forbid their existence. But this is a cold comfort, a victory of physics that says nothing of biology. A stable orbit is merely a stage. It is not the play itself. Survival is not the same as life, and for that a world needs more than just a predictable path. It needs warmth, it needs energy, it needs the gentle, persistent kiss of starlight consistent enough to melt ice and sustain the delicate chemistry of existence. For decades this seemed like the true insurmountable barrier, a puzzle far more complex than gravity. Imagine trying to warm yourself by two bonfires that are constantly circling each other. Sometimes they stand together a unified wall of heat. Other times they are on opposite horizons, their warmth diluted by distance. A planet caught in this cosmic dance would experience not a steady life-giving stream of energy, but a volatile pulsating torrent. One moment it's seared by the combined fury of two suns. The next it's plunged into a deep chill, as one star eclipses the other, or as its own eccentric orbit carries it far into the cold. The traditional Goldilocks zone, that serene temperate ring around a single star where water can flow freely, seemed to dissolve into utter chaos here. How could life possibly arise, let alone thrive, in a place where the very definition of day and year was subject to a celestial whim, where summer and winter were not dictated by a simple axial tilt, but by a dizzying three-body ballet? The problem was simply too complex for back-of-the-envelope calculations. It was a storm of variables, the masses of the two stars, the shape and period of their orbit around each other, the planet's own path, its atmospheric composition, its reflectivity. To solve it, to truly map the climate of a world with two suns, we needed a new kind of laboratory. We couldn't build one, so we had to dream one into existence. We turned to the silent thinking hearts of our most powerful supercomputers, tasking them with creating not just one alien world, but millions. Inside these digital crucibles we could forge virtual solar systems specifying the exact nature of the twin stars, a hot blue giant paired with a cool orange dwarf, or two sun-like twins in a tight embrace. We could then sprinkle planetary seeds throughout these systems, and command the simulation to run not for days or weeks, but for millions, even billions of virtual years. What we were asking these machines to do was monumental. For every single point on a planet's surface, for every second of its simulated life, the computer had to calculate the incoming energy. It had to track the light from star A, accounting for its distance and angle. Simultaneously, it had to track the light from star B, doing the same complex trigonometry. It had to figure out when one star blocked the other, when the planet's own rotation created dawn or dusk, and how the atmosphere would trap and circulate the bizarre patterns of incoming heat. We were essentially building ghost worlds from mathematics and light, allowing us to watch the climate evolve over eons, fast-forwarding, through geologic time to see if any corner of these chaotic systems could ever know a moment's peace. It was a search for a harbour in a hurricane, a quest for climatic stability in the most unstable of settings. At first, the results were just as we feared: climatic mayhem. We watched planets freeze and boil in a geological instant. We saw oceans flash into steam as the two suns aligned in the sky, their combined power scorching the surface, only to have those same oceans freeze solid as the planet was flung out to the system's aphelion, the farthest, coldest point in its path. The habitable zone wasn't a stable ring, it was a flickering, treacherous mirage. It swelled and shrank, warped and twisted with every turn of the binary stars. It breathed inhaling and exhaling with the rhythm of their orbit. For any given planet, the time spent within this fleeting zone of warmth was often too short, too unreliable to allow the slow, patient miracle of life to take hold. The initial data painted a grim picture of beautiful, intricate, but ultimately sterile solar systems. But science is a discipline of patience. We refined the models, expanded the parameters, and let the simulations run longer, exploring a wider variety of stellar configurations. And then slowly, from the heart of this gravitational and thermal tempest, something unexpected blossomed. Amidst the chaos, patterns began to emerge. The computer screens, once filled with flashing reds of too hot and deep blues of too cold, began to show persistent, stable bands of temperate green. It turned out that our initial intuition was incomplete. We had underestimated the universe's capacity for creating stability from complexity. We had found them, not just stable orbits, but stable climates. The habitable zones in binary systems were real. For a planet in a wide circumbinary orbit, a P-type world circling far beyond the central stellar duo, the situation became surprisingly simple. From this great distance, the two stars locked in their tight central dance began to behave as a single combined point of light. The planet wouldn't perceive two distinct moving heat sources. Instead, it would be warmed by a single, massive, blended light star at the heart of its system. This central sun might flicker slightly in its total energy output, as the two stars eclipsed one another from the planet's perspective, creating a gentle rhythmic pulse of warmth across the ages. But these variations were often minor, not nearly enough to disrupt a global climate. An expansive, serene and perfectly stable habitable zone could form a vast ring around this binary heart, a cosmic invitation for worlds to form and life to flourish, warmed by the steady glow of two suns acting as one. The discovery was breathtaking, fundamentally redrawing the map of cosmic real estate. It meant that any binary system with stars orbiting closely together could host a family of potentially life-bearing planets in wide, stable orbits just like a single star. The chaotic dance was confined to the center stage. In the cheap seats far away, the universe was perfectly calm. But it was the other configuration, the S-type, or circumprimary orbit, that held the deepest surprise. This is a world that orbits just one of the two stars, treating the second more distant star as a kind of wandering luminous moon. Here the gravitational interference is immense, and it was here that we assumed the climate would be most violent. The models, however, told a different story. They showed that if the companion star was far enough away, its influence became secondary, a subtle addition rather than a disruptive force. A planet could orbit its primary sun within a completely conventional habitable zone, receiving the vast majority of its warmth from this single steady source. The distant companion would drift through its sky sometimes for months or years at a time, a brilliant but remote beacon. It wouldn't provide enough heat to boil the oceans, but it would provide some. Its contribution would be like a persistent, gentle twilight supplementing the primary star's energy. In a profound way, the companion star would act as a climatic stabilizer. As the planet orbited its main sun, its own axial tilt would create seasons, but the distant light of the second sun would soften the blow of winter, preventing runaway glaciation in the polar regions. It would provide just enough extra energy to keep the planet's thermostat from dropping too low, effectively widening the habitable zone and making the climate more stable, not less. This revelation was a complete reversal of our expectations. The very feature we thought was the ultimate deal-breaker, the presence of a second star, could in some cases be a life-sustaining advantage. But the true paradigm shift came when we stopped thinking about the stars as simple sources of heat and started considering the quality of their light. A star's energy is not generic. It is delivered across a spectrum of wavelengths, a unique colour signature determined by its temperature and composition. Our sun's yellow-white light is rich in the wavelengths that chlorophyll, the engine of life on Earth, has evolved to capture. But what if a planet had two different kinds of light to work with? Imagine a world orbiting a G-type star like our Sun, but with a distant companion, a smaller, cooler and much redder M-dwarf star. For much of its day, the planet is bathed in the familiar full-spectrum light of its primary. But as that sun sets, the sky doesn't fall into darkness. Instead, it deepens into an endless ruddy twilight, illuminated by the crimson glow of the secondary star. Life on such a world would never know true night. It would exist in a perpetual cycle of bright yellow day and dim red evening. What kind of photosynthesis could evolve there? You might see plants with two different types of photosynthetic pigments. One like our chlorophyll, designed to efficiently capture the energy from the main sequence star. Another a deep purple or black pigment specialized to absorb the long, low-energy wavelengths of the red dwarf. Such a biosphere would be incredibly resilient and productive. It wouldn't have to shut down for half of every rotation. It could be harvesting energy, growing and producing oxygen around the clock. The very rhythm of life would be different, tuned not to a simple cycle of light and dark, but to a more complex cadence of bright gold and deep crimson. This opens up entirely new biochemical pathways, new evolutionary strategies. The dual sun environment, far from being a liability, could be an incredible evolutionary driver pushing life towards greater efficiency and complexity. It presents not a problem to be overcome, but an opportunity to be exploited, and the potential advantages kept revealing themselves in the simulations. We considered the problem of stellar flares, the violent, unpredictable eruptions of high-energy radiation that can strip a planet's atmosphere and sterilize its surface. Young active stars are particularly prone to this, and many red dwarfs, the most common stars in the galaxy, are notorious for their violent tempers. A planet orbiting such a star would face a constant threat of annihilation. But what if it had a companion? What if that companion was a larger, more stable star? In such a system, the companion could act as a celestial guardian. As the two stars orbit, there would be predictable periods where the large, gentle star would pass directly between the planet and its volatile primary. During this stellar eclipse, which could last for days or even weeks, the planet would be completely shielded from any lethal flares. Life on such a world might evolve to synchronize its most delicate reproductive cycles with these periods of cosmic sanctuary. The binary system, once seen as a source of chaos, now becomes a clockwork shield, a predictable celestial event that makes the universe a safer place. Furthermore, the complex gravitational tides raised by two stars could be a powerful engine for planetary life. On Earth, our moon's pull creates ocean tides, but the gravitational kneading from two separate stars would be far more intricate. This constant flexing could generate immense tidal heating within the planet's core, keeping it volcanically active for billions of years longer than it otherwise would be. This activity is crucial for life. It drives plate tectonics, recycles essential minerals, and powers the magnetic field that protects the atmosphere from being stripped away by the stellar wind. The binary dance becomes a gravitational gyroscope spinning a planet's molten heart and sustaining the very conditions that allow life to persist on its surface. Each of these discoveries, each simulation result pointed toward the same staggering conclusion. We had been looking at the universe with one eye closed. We had focused so intently on systems that mirrored our own, a single stable star, that we dismissed the majority of stars in the galaxy as inhospitable. Binary and multiple star systems make up more than half of the stellar population. By writing them off, we were ignoring trillions of potential homes for life. These complex dynamic systems are not cosmic curiosities to be dismissed. They are a vast, unexplored frontier of possibility. The complex light, the gravitational shielding, the tidal heating. These are not mere quirks. They are potentially powerful new ingredients in the recipe for life, ones we have only just begun to understand. The map of where we might find a second genesis, a separate independent origin of life, has been fundamentally redrawn. The search is no longer confined to the quiet suburbs of single suns. It has been thrown wide open into the bustling dynamic downtowns of binary systems. The number of potential candidates for habitable worlds in our galaxy didn't just double. It may have increased by an order of magnitude. Our simulations have shown us that nature is far more clever than we ever gave it credit for. Chaos and order are not always enemies. Sometimes from the most complex and violent of dances, the most stable and beautiful possibilities can emerge. We have found the stage. We have begun to understand the intricate and varied light that would fall upon it. Billions upon billions of silent invitations previously hidden in plain sight have suddenly been revealed across the cosmic ocean. But this raises a profound and tantalizing new question. If these stages are indeed set, what kind of players would evolve under the ceaseless gaze of two suns? So we have found our prize. A world that has threaded the needle of orbital mechanics, settling into a stable, life-sustaining embrace with not one but two suns. After navigating a cosmic minefield of gravitational chaos, we have arrived at a place of astonishing possibility, a planet where liquid water could trace rivers across continents under a sky of perpetual twilight or blazing double noon. It is a moment of profound triumph, the theoretical peak of our journey. But here at the summit, the air grows thin and the view down the other side is terrifying. For stability is not the same as safety. The same physics that permits this world's existence now presents it with a series of trials so severe they make Earth's most violent epochs seem like tranquil garden parties. The delicate dance of this twin-sun world is not a gentle waltz. It is a frantic tango on the edge of a volcano, a performance where a single misstep means oblivion. The first most immediate danger arrives not as a gentle warmth, but as a fusillade of stellar rage. Our own sun, a relatively calm and predictable star, occasionally throws tantrums. We call them solar flares, colossal eruptions of magnetic energy that hurl billions of tons of charged particles into space at nearly the speed of light. On Earth, our powerful magnetic shield deflects the worst of this onslaught, treating us to the sublime spectacle of the aurora. But in a binary system, you're caught in a cosmic crossfire. Imagine your world turning serenely on its axis, being broadsided by a wave of searing plasma from one star. The atmosphere shimmers, the magnetic field groans under the strain, and a curtain of ghostly light engulfs an entire hemisphere. But there is no night side for refuge. As your planet rotates the blasted hemisphere, turning away from its tormentor, it may turn directly into the path of an entirely different storm unleashed by the second sun. There is nowhere to hide. This world is a target in a shooting gallery with two barrels, and both are perpetually loaded. This relentless bombardment is more than just a light show. It is an existential threat to the very air you would breathe. Each superflare acts like a celestial blowtorch, carrying the potential to heat the upper atmosphere and methodically strip it away, molecule by molecule, bleeding the planet's lifeblood into the void over millions of years. For life to even begin, this world would require a magnetosphere of unimaginable power, a planetary force field so robust it could withstand a siege from two directions at once. But the chaotic gravitational tug-of-war that this planet endures could actively work against the formation of such a shield. A strong magnetic field is generated by the churning of a molten metallic core, a kind of planetary dynamo. Could such a dynamo remain stable and strong when the entire world is being constantly squeezed and stretched by the gravity of two separate suns? It's a terrible paradox. The very conditions of its birth might rob this world of the one defense it needs most to survive its own parents. Many binary systems, especially those compact enough to host a stable planet, involve at least one red dwarf. These M-type stars are the most common in the galaxy, long-lived and seemingly gentle. But this is a devastating deception. Red dwarfs are notoriously volatile, especially in their youth, prone to flares that can be thousands of times more powerful than our suns. A planet orbiting in the habitable zone of a red dwarf is already living on a knife's edge. Now place that planet in a system with another star, perhaps a brighter sun-like companion. You have created a nightmare scenario. One sun provides the steady warmth for liquid water, while the other, the supposedly dimmer sibling, periodically bathes the world in sterilizing blasts of high-energy X-rays and ultraviolet radiation. Surface life would be an impossibility. Any organism would be scoured from the land, its complex cellular machinery torn apart by invisible rays. Life's only hope would be to retreat to become a creature of the deep, cowering in the crushing dark of its own oceans, forever shielded from the wrathful gods in its sky. Even if life could somehow endure this radiant fury, it would face a more insidious, more psychologically destabilizing challenge, the complete absence of reliable time. On Earth, life's rhythms are set by an ancient and unwavering clockwork. The stately procession of day and night, the predictable march of the seasons. These cycles are woven into the DNA of every living thing, dictating when plants grow, when animals migrate, when we ourselves feel the urge to sleep and wake. We are children of cosmic regularity. On a planet with two suns, this fundamental metronome is shattered into a million chaotic pieces. The planet's orbit is not a simple, clean ellipse. It is a complex, looping, spiraling path, a three-dimensional dance we call a quasi-periodic orbit. From the surface, you would witness a sky that is never the same from one day to the next. Imagine a sky where one sunrise is a familiar golden orb, only to be joined hours later by a second, perhaps a fiery crimson companion, appearing from a different point on the horizon. Their paths would intersect, overlap, sometimes moving in tandem, other times in opposition. The very concept of noon would become meaningless. Would it be the moment one sun is highest in the sky, or the moment both are? What if they are on opposite sides of the sky, creating a shadowless omnidirectional glare? There would be days of intense searing double light, followed by long, drawn-out periods of eerie twilight as one sun sets long before the other. There might be no true night at all for millennia, only for the planet's shifting orbit to then plunge it into a prolonged frigid darkness, where both suns are mere specks in a frozen sky. The analemma, the lazy figure 8 our sun traces in the sky over a year, would be replaced by a celestial scribble, an unpredictable, terrifying pattern of light and heat. This is not a mere aesthetic curiosity. It is a recipe for climatic catastrophe. The amount of energy a planet receives from its stars, its insolation, is the primary driver of its climate. On our twin-sun world, this energy input would be subject to wild erratic fluctuations. As the planet swings closer to one star on its convoluted path, it might experience a proto-summer, a gentle warming, but then its orbit could carry it on a trajectory that brings it close to both suns simultaneously. The effect would be devastating. A double summer of unimaginable intensity where global temperatures soar, baking continents, and potentially boiling the surfaces of shallow seas. This searing heat wave wouldn't be a season. It would be an orbital event unpredictable in its timing and duration. It would be followed just as unpredictably by a deep winter as the planet swings far out from both stars, its surface plunging into a desperate cold that could encase entire oceans in ice. These are not seasons. They are thermal seizures. Life on Earth evolved to handle predictable change. Bears hibernate through winter because winter always comes. Birds fly south because they know the north will grow cold. But how could life evolve in a system with no reliable when? How could a plant know when to flower if the frost might return at any moment, or if a global heat wave could scorch it before it ever bears fruit? The entire evolutionary strategy of adaptation to cycles would be useless. Instead of adaptation, life would require a kind of permanent, desperate resilience. Perhaps plants would evolve to reproduce explosively all at once, in the brief moments of temperate calm, their seeds lying dormant for centuries waiting for the next fleeting window of opportunity. Animals might need to enter states of suspended animation not for a season, but for an eon, their metabolisms shutting down almost completely to ride out the long chaotic swings between fire and ice. The atmosphere itself would be a monster. The extreme temperature differences across the planet, one hemisphere scorched by a close pass with the sun while the other is in frigid shadow, would create pressure gradients of unimaginable power. The result would be storms that would make Jupiter's great red spot look like a summer squall. We are not talking about hurricanes. We are talking about global bands of wind screaming across the surface at supersonic speeds. We are talking about continent-sized cyclones that never dissipate but merely merge and feed off the planet's thermal chaos. Rain, if it fell, would be a torrential, world-drowning deluge capable of carving Grand Canyons in a single afternoon. The very air would be a force of erosion, a relentless sandblaster scouring the planet's surface down to bedrock. Forget lush forests or sprawling grasslands. The landscape of this world might be one of stark, wind-blasted rock, a testament to an atmosphere at war with itself. And beneath the surface, a different kind of violence would hold sway. The same gravitational forces that choreograph the planet's dance also inflict a constant grinding punishment upon its very structure. We feel the gentle pull of our moon in the ocean tides. Now imagine replacing the moon with an object 333,000 times more massive our sun, and then add a second one. This planet is caught in a gravitational vice. The world is being perpetually kneaded like dough its rocky mantle, and crust stretched and compressed by the competing pulls of its two stellar masters. The consequence would be a level of geological instability that is difficult to comprehend. Plate tectonics, the slow engine of change on Earth, would be supercharged into a frantic, chaotic frenzy. Earthquakes would not be isolated events. They would be a constant shuddering tremor in the rock, a planetary fever that never breaks. Volcanoes would likely pockmark the entire surface, not just along tectonic boundaries, but everywhere, as the immense tidal heating from within forces magma, up through any available fissure. This world would live in a state of perpetual eruption, its atmosphere choked with sulfur and ash, its continent eternally remade by fire. This internal heating is another of the system's cruel paradoxes. A little of it can be good, keeping a planet's core molten and its magnetic shield active, but too much, and you trigger a runaway greenhouse effect. The endless volcanism pours carbon dioxide and other heat-trapping gases into the atmosphere far faster than any geological process can remove them. The planet heats up, causing more water to evaporate, which traps even more heat, which in turn could trigger even more volcanism. It's a feedback loop from hell, a one-way ticket to becoming a Venus-like pressure cooker, shrouded in a toxic, suffocating atmosphere, its surface hot enough to melt lead. The very forces that allow the planet to exist conspire to sterilize it. Any chance for life is a tightrope walk over a sea of molten rock under a sky of acid rain. Finally, there is the unseen assault, a constant invisible hurricane that flows from both suns, the stellar wind. This is not wind in any terrestrial sense, but a ceaseless torrent of protons and electrons, the very substance of the stars themselves, flowing outwards into space. On Earth, our magnetosphere carves a protective bubble, the heliosphere deflecting this cosmic radiation. But in a binary system there are two stellar winds. These two torrents of particles rage across the system until they collide, creating a vast, turbulent and highly energized boundary, a shock front. Our beleaguered planet, in its looping irregular orbit, would have to pass through this violent frontier again and again. Each passage would be like flying an airplane through the sound barrier, a moment of intense buffeting and energetic bombardment. This constant shock would be yet another force trying to strip away the planet's precious atmosphere, another layer of radiation for life to contend with. The very space between the planets is not empty. It is a battleground, and this world is trapped directly on the front line. Flares a chaotic climate tidal volcanism and warring stellar winds. This is the gauntlet that any form of life must run. So what kind of being could possibly arise from such a crucible? It would have to be a masterpiece of biological engineering, a creature forged in fire and chaos. Its very cells would need defences against radiation that we can only dream of, perhaps equipped with redundant sets of genetic material, so that if one strand is shattered by a cosmic ray, a backup is ready to take its place. It might possess enzymes of miraculous efficiency, capable of repairing DNA damage almost instantaneously. Or perhaps its life chemistry would not be based on fragile carbon at all, but on sturdy crystalline silicon, forming the basis for a creature more like a living rock impervious to heat and radiation. Its metabolism would have to be the ultimate in flexibility. Unable to rely on a steady supply of sunlight, it might evolve to be a facultative photosynthesizer, generating energy from light when available, but seamlessly switching to chemosynthesis when its suns disappear, drawing sustenance from the chemical energy of volcanic vents at the bottom of a dark ocean. It wouldn't just hibernate for a season, it would be capable of estivation on a geological timescale, shutting down its life processes to a bare flicker to survive a 1,000-year winter or a searing double summer. It would be a master of patience, a living time capsule waiting for the storm to pass. Structurally, it would be a fortress. To withstand the gravity tides and the planet-scouring winds, life would likely be low to the ground, hunkered down with powerful root systems, or exoskeletons of incredible tensile strength. Tall, delicate forms would be an evolutionary impossibility. Imagine sprawling lichen-like superorganisms that cling to the wind-blasted rock, or armoured crab-like beings that can brace themselves against the perpetual earthquakes. Life here would not reach for the sky in aspiration. It would cling to the ground in desperation. Think for a moment what it would be like to be a sentient being born on such a world. Your consciousness would be forged in a universe of profound and violent uncertainty. The sky for us, a source of poetry and wonder, would be for you a canvas of dread, a source of capricious violence. Your gods would not be benevolent entities of light, but gods of chaos, fire and fury. Your entire culture, your science, your philosophy would be built not on the presumption of order, but on the bedrock of survival, against a cosmos that seems actively hostile to your existence. Your ancestors would not have looked to the stars to navigate, but to find shelter. The blueprint for life in a binary system is demanding a list of specifications so extreme it borders on the impossible, and yet the universe is not constrained by our imagination. Its capacity for creation is boundless. Every challenge we have outlined is also an evolutionary opportunity. Every deadly threat is a crucible that could forge life of unimaginable resilience and complexity. The downward path from the peak of possibility is steep and treacherous, littered with the ghosts of worlds that failed the test. But if against all of these colossal odds, a single spark of life took hold on such a planet, if it survived, the radiation endured the chaos and rose to consciousness under the light of 2 suns. What a strange and magnificent testament to the tenacity of existence that would be. What wonders might await us in that sky, that is so unlike our own, and so we are left suspended between 2 fires caught in a gravitational crosscurrent that seems to promise only annihilation. We have journeyed through the chaos, witnessed the brutal mechanics of worlds torn by tidal forces, and felt the searing radiation from a relentless stellar duo. The logical conclusion appears inescapable that such a system is a cosmic tomb, a place where the seeds of life are scorched before they can ever sprout. It seems a definitive if disheartening answer to our central question. But what if we have been asking the wrong way? What if we have been viewing this violent, chaotic dance through the narrow lens of our own fragile existence? The universe, after all, has a habit of defying our expectations of nurturing life not in the gentle cradles we predict, but in the very furnaces we deem impossible. Perhaps the fury of 2 suns is not a barrier to life but a catalyst for it. Perhaps it is the ultimate crucible forging beings of such resilience and ingenuity that they would perceive our own quiet, solitary sun as a pale and uninspiring whisper. Before we surrender to the physics of destruction, we must turn our gaze back to the only place we know life exists, not to its peaceful gardens, but to its most savage frontiers. Here in the deepest trenches of our own oceans, where the pressure could crush a submarine and the darkness is absolute, we find life. Not just surviving, but thriving. Entire ecosystems are powered not by sunlight, but by the chemical breath of the planet itself, clustered around volcanic vents that spew a cocktail of superheated toxic minerals. These are the chemotrophs, biological alchemists that metabolize sulfur and metals, weaving a food web from ingredients that would poison nearly every surface dweller. You have to ask yourself, what would these creatures make of a sun at all, let alone 2? Their existence is a profound testament that the energy for life need not rain down from above, it can well up from within. Now transport that principle to a tidally heated world in a binary system, a planet kneaded and stretched by the gravity of its twin stellar masters. Its core could be kept molten and active for eons, creating a vast network of subterranean vents, a planetary circulatory system of chemical energy. Life there might never need to see the sky. It could flourish in a dark, warm global ocean, utterly oblivious to the stellar tempests raging on the surface, its evolution driven by geology rather than astronomy. But what if life does brave the surface? What if it chooses to face the dual onslaught of light and radiation head-on? On Earth we have the humble tardigrade, the water-bearer microscopic creature of almost mythical resilience. We can freeze it to near absolute zero boil, expose it to the vacuum of space and bombard it with doses of radiation 1,000 times more lethal than what would kill a human. It simply curls into a desiccated ball, a state of suspended animation called cryptobiosis, its cellular machinery protected by unique proteins. When conditions improve, it rehydrates and carries on as if nothing happened. This isn't just survival, it is defiance. Now imagine this principle scaled up, evolved over 1 billion years under the harsh glare of 2 stars. Picture an organism that doesn't just endure radiation, but has woven that endurance into the very fabric of its being. It might possess layers of biological shielding, a hide infused with metallic compounds harvested from the soil. Its cells could contain redundant copies of its genetic code, a living library, from which to repair any damage from high-energy particles. These beings would not fear the solar flares from their suns. They would simply weather them, their entire biology, a fortress built to withstand the siege. This concept of biological adaptation extends to the most fundamental process of all harnessing the light itself. On Earth, photosynthesis is tuned to our single G-type star. Chlorophyll, the pigment that powers most of our biosphere, is brilliant at absorbing red and blue light, but it reflects green, the very colour that our sun emits most intensely. It's an effective but strangely inefficient system. In a binary system with, say, a brilliant yellow-white star and a dim brooding red dwarf, a single pigment like chlorophyll would be woefully inadequate. It would be like trying to listen to a symphony with an ear tuned to only a single note. Life, however, is a master composer. It would not settle for such a limitation. We can envision flora possessing a far more sophisticated biochemical toolkit, a palette of pigments designed to capture the full spectrum of its celestial environment. Imagine forests of towering crystalline structures, their leaves shimmering with an iridescent black, a colour chosen not for aesthetics, but for supreme efficiency. This blackness would be the result of multiple pigments layered together, one optimized for the high-energy photons of the brighter star, another perfectly tuned to the low-energy infrared-rich light of its dimmer companion. As the twin suns chart their complex paths across the sky, different pigments could become active, allowing the plant to track and absorb energy with relentless precision. Perhaps these plants wouldn't even be a static colour. They could be chromatically dynamic, shifting from a deep violet in the dual morning to a metallic red as the dwarf star dominates the sky, their entire physiology, a living solar panel constantly recalibrating itself to the shifting celestial tides. The energy budget of such a world would be immense, a continuous feast of photons from two distinct sources. This could fuel a biosphere of incredible richness and complexity, with growth rates and biological activity that would make our own temperate forests seem sluggish and muted by comparison. Life wouldn't just be surviving here, it would be supercharged. Yet even with such ingenious photosynthesis, the sheer violence of the radiation remains a formidable obstacle. An unprotected planet would be sterilized. But who is to say the planet would be unprotected? We often think of a planet's atmosphere as a static geological feature. But on Earth, our own atmosphere has been profoundly shaped by life itself. The Great Oxidation Event 2 billion years ago saw tiny cyanobacteria slowly terraform our entire world, pumping out oxygen that created the ozone layer, our essential shield, against solar ultraviolet radiation. Life did not find a sanctuary, it built one. Now apply that transformative power to a world with two suns. The selective pressure to create an atmospheric shield would be exponentially greater. We can hypothesize the evolution of microorganisms that perform a kind of bioatmospheric engineering. Perhaps they consume certain minerals from the crust and release a specific durable gas, one far more effective at blocking X-rays and charged particles than ozone. This process could create a feedback loop. As life evolves, it thickens the atmospheric shield. As the shield thickens, it allows more complex life to emerge, which in turn contributes even more shielding gases to the atmosphere. Over geological timescales, the planet's inhabitants would have constructed their own salvation, a bespoke multi-layered atmospheric aegis tailored perfectly to the specific radiation signatures of their two stars. The sky of such a world might not be blue. It could be a permanent hazy gold or a deep misty orange, the colour of a perpetual sunset. To stand on its surface would be to exist under a celestial dome built by life itself, a testament to the power of biology, to not merely adapt to its environment, but to seize control of it, transforming a death zone into a thriving, protected paradise. Visitors from Earth would find the air thick, heavy, and filled with strange aerosols, but to the natives it would be the very breath of their world, a collective exhalation that holds the fury of their suns at bay. The challenges, however, are not just radiative, they are gravitational. We've seen how the orbits of such planets can be eccentric, leading to wild, unpredictable swings in temperature from deep freeze to scorching inferno. The very concept of seasons, a gentle, predictable cycle on Earth, would be replaced by a chaotic rhythm of climatic extremes. How could any organism possibly adapt to a world where a pleasant spring could be followed by a decade-long winter, or a flash summer that boils the seas? The answer once again may lie in life's extraordinary ability to manipulate time. Hibernation and dormancy are common strategies on Earth, but a binary world might push them to their absolute limits. We can imagine creatures that have perfected the art of suspended animation not for a single winter, but for centuries. These beings might live in vast communal burrows, their metabolism slowing to a near-complete stop as their planet swings out to the cold, distant apastron of its orbit. They would be living fossils sleeping through the long, lean years, their biological clocks synchronized not to the rotation of their planet, but to the grand, sweeping arc of its multi-century journey through space. Then, as the orbit carries the planet back into the warmth of its twin suns, a planetary scale awakening would occur. The world would transform from a frozen ball of ice into a riot of life in a matter of years. Plants would erupt from the permafrost, and the dormant creatures would emerge to feast, breed, and live their entire active lives in a compressed, frantic burst of activity before the long winter returns. Their life cycle would be a dramatic dance of patience and explosion. Alternatively, life could become nomadic on a scale we can barely comprehend. If the temperate zones of the planet are not fixed but instead migrate across the globe with the shifting orbits, then life would learn to follow. Imagine continent-sized herds of colossal grazers or entire floating ecosystems of aerial life forms, forever chasing the zone of comfort. Their existence would not be tied to a place but to a condition. Their migrations would be epic, guided by a deep instinctual understanding of the complex gravitational mechanics of their system, a celestial ballet of survival, where to stand still is to perish. These adaptations, while extraordinary, are still extrapolations of biology as we understand it. They are based on carbon and water, on cells and DNA. But the most profound possibility, the one that truly opens the door to the unimaginable, is that in such an alien context, life itself might follow a different set of rules entirely. The sheer environmental pressure of a binary system could be the very thing that favours a biochemistry, fundamentally different from our own. Perhaps carbon, the flexible backbone of terrestrial life, is too fragile. In a world with extreme temperature fluctuations, perhaps silicon-based life would have the edge, its stronger chemical bonds providing the stability needed to endure. The creatures of such a world would be beings of crystal and rock, slow, deliberate, and almost geological in their nature, their thoughts measured in millennia, their bodies built to last. And what of the mind? How would consciousness evolve on a planet that may have no true consistent night, where the sky is always lit by at least one sun, and sometimes by the overwhelming glare of two, our own cycles of sleep and wakefulness? Our very sense of the passage of time are tied to the simple, predictable rhythm of a single sun. An intelligence born under a dual gaze might perceive reality in a completely different way. With no period of universal darkness, the concept of a collective unconscious might take on a literal meaning. Perhaps life would develop a form of photosynthetic consciousness, a state of being where thought is directly fueled and modulated by the changing light of the two stars. The brighter yellow sun might inspire active logical thought, while the dimmer red sun could evoke a more contemplative, intuitive state of mind. In such a world, a solar eclipse when one star passes in front of the other wouldn't just be an astronomical event. It would be a profound shared psychological experience, a momentary shift in the very fabric of thought for every sentient being on the planet. We stand at the edge of our own understanding, peering into the dazzling light of a hypothetical world. We have catalogued the dangers, the radiation, the gravitational chaos. But at every turn we find a counter-argument not in physics but in biology's relentless creativity, where we see a fatal dose of radiation life devises a shield, where we see an unstable energy source life evolves a dual intake engine, where we see a chaotic climate life learns to dance with the rhythm or to sleep through the storm. The question then ceases to be, can life survive here? And instead becomes, what magnificent, unimaginable forms might it take? The two suns are not a death sentence. They are a challenge. And if there is one constant we have observed in the cosmos, from the scalding vents of our own seabed to the frozen expanse of interstellar space, it is that life in its infinite and stubborn ambition always rises to the occasion. The universe is not a series of quiet, safe harbours. It is a vast dynamic arena of problems awaiting solutions, and life under one sun or two is the ultimate problem solver. And so our long voyage across the sea of interstellar night from one flickering stellar flame to the next draws to a close. We began this journey shadowed by a profound and ancient skepticism, a deeply ingrained assumption inherited from centuries of looking up at our own solitary sun. We saw the cosmos through a singular lens, believing that the serene, predictable solitude of a star like our own was the sole crucible in which the delicate chemistry of life could be forged. Binary systems in this old and tired narrative were the homes of chaos. They were gravitational demolition zones, celestial maelstroms where planets were either torn asunder or flung into the frozen abyss, their potential for life extinguished before it could even begin. They were cosmic curiosities, beautiful but barren, the waltzing partners of a destructive ballet, not the nurturing parents of worlds. Yet with every world we have visited on this odyssey of the imagination, with every intricate simulation we have witnessed, and every pioneering discovery we have examined, that monolithic assumption has been systematically dismantled piece by piece. We have watched as the ironclad laws of physics, once seen as a barrier, revealed themselves to be the authors of an unexpected stability. We've learned that nature's genius for equilibrium is far more profound, far more creative than our terrestrial intuition could have ever predicted. The frantic, fiery dance of two suns does not necessarily preclude life. It merely sets a different kind of stage with a different kind of light. It demands a different kind of resilience, a different kind of evolution, and in doing so, it opens up possibilities that we are only now beginning to grasp. The very definition of a habitable world, a concept we once held so tightly, has been irrevocably broadened, its borders pushed into territories we once labelled as impossible. The Goldilocks zone is no longer a simple static ring encircling a single placid star. It has become a dynamic breathing volume of space, a shimmering amorphous region that swells and contracts with the combined energy of two stellar hearts. We've seen how a planet in a circumbinary orbit, a true Tatooine, could trace a path through a zone of habitability far wider and more forgiving than the one our own Earth inhabits. Its twin suns, working in concert, could moderate the climate their gravitational tugs and pulls, preventing the catastrophic runaway freezing or boiling that can doom a world on the edge of a conventional habitable zone. The seasons on such a planet would be epics written not by a simple axial tilt, but by the grand celestial mechanics of its entire system. Imagine a great summer that lasts for decades, when the planet's wide orbit brings it closer to the combined radiance of its parent stars, followed by a long, gentle autumn as it sweeps back out into the cooler twilight. Life there would not just adapt to this rhythm, it would be born of it. Its cycles of hibernation, migration and procreation would be woven into this grand cosmic clockwork. Its very biology might carry the imprint of two suns, perhaps evolving dual forms of photosynthesis to harness different wavelengths of light, or developing complex sensory organs to navigate a world of shifting shadows and double dawns. This fundamental re-evaluation extends to the very core of our search for ourselves in the universe. For decades, the search for extraterrestrial intelligence SETI has been predicated on a simple, understandable bias looking for a reflection of us. We have pointed our radio dishes primarily towards G-type main-sequence stars, yellow dwarfs, so similar to our Sun that we call them solar analogues. We were searching for Earth's twin, orbiting a clone of our own star, believing this to be the most logical, most probable place to find a familiar voice calling out across the static of the cosmos. But this journey has forced us to confront the breathtaking narrowness of that perspective. We have been looking for a single lighthouse in an ocean of binary systems which constitute more than half the stars in our galactic neighbourhood. What if we have been listening to the wrong channels, looking in the wrong corners of the sky? What kind of civilization might arise under the perpetual gaze of two suns? Their mythology would not speak of a single monolithic sun god, but of divine twins of warring brothers or loving partners painting the sky. Their fundamental understanding of time would be immeasurably more complex than our own, shaped by the intricate interplay of multiple orbital periods, their days, nights and years defined by a cadence we can barely model. Their science, particularly their grasp of gravity, would be innate, intuitive. A child growing up on such a world would understand orbital mechanics not as an abstract concept in a textbook, but as a tangible daily reality, as plain to see as the double shadows stretching across their alien landscape. And if such a civilization chose to communicate to send a signal, would they broadcast continuously, as we have naively attempted, Or would they time their transmissions to celestial events of great significance? Perhaps they would only broadcast when their two suns align in the sky from our perspective, an event known as an ecliptic conjunction, creating a cosmic flare, a signpost. Or maybe they would use the immense gravitational lensing of their own stars to focus a beam of information directly at promising nearby systems. We must now consider that an intelligent signal from a binary system might not be a steady, monotonous beacon, but a complex, modulated pulse, its very structure, a message reflecting the dual nature of its home. Our search must evolve. It must become more sophisticated, more patient, embracing the beautiful complexity that these systems represent. We must begin to listen for the symphonies, not just the solos. This grand expansion of our cosmic imagination is not merely a philosophical exercise. It is the driving force behind a new generation of technological marvels, the eyes and ears that will turn these tantalizing possibilities into hard data. We are standing at the dawn of an unprecedented era of discovery. The James Webb Space Telescope, now gliding silently through the darkness 1,000,000 miles from Earth, is not just an observatory. It is a time machine and a chemistry lab combined. Its exquisite sensitivity to infrared light allows it to pierce the dusty veils of stellar nurseries to watch as planets are born within the swirling protoplanetary disks of binary stars, witnessing firsthand whether these systems are indeed planet killers or cradles. More importantly, when one of these distant worlds passes in front of its parent stars, Webb can perform an analysis of breathtaking precision. As that combined starlight filters through the planet's atmosphere, air molecules will absorb specific frequencies of light, leaving tiny dark lines in the spectrum. These lines are chemical fingerprint signatures of the gases present. Webb is looking for the familiar markers of life: oxygen, a byproduct of photosynthesis; methane, a potential sign of metabolic processes; water vapor, the indispensable solvent. But in a binary system, the challenge and the opportunity is magnified. The intense and varied ultraviolet radiation from two stars, especially if one is more active, could produce a host of atmospheric chemicals that might mimic biosignatures, creating false positives that could lead us astray for years. Conversely, this unique radiation environment might foster a biochemistry that produces entirely different gases, biosignatures our terrestrial models would never predict. Discovering an atmosphere rich in, for example, chlorine-based compounds alongside methane might be dismissed as industrial pollution on an Earth-like world, but could be the telltale sign of a truly alien biology on a planet orbiting a K-dwarf and a white dwarf. Webb is our first great tool for untangling this incredible complexity, and it is only the beginning. On the drawing boards and in the dreams of engineers and astronomers, the next wave of great observatories is already taking shape. Missions currently conceptualized under names like the Habitable Worlds Observatory are being designed with one primary purpose, not just to find planets, but to characterize them. These future space telescopes will be armed with advanced coronagraphs and starshades, enormous intricate devices designed to block the overwhelming glare of a planet's parent stars. Imagine trying to spot a firefly next to a searchlight from miles away. That is the scale of the challenge. By suppressing the starlight by a factor of billions, these instruments will for the first time allow us to take a direct photograph of an Earth-sized exoplanet. We will see a pale blue dot, or perhaps a pale red one, or a mottled green and brown one orbiting not one but two distant points of light. It will be a watershed moment in human history the day another Earth resolves from a mere data point into a tangible place, a world with continents, oceans, and clouds. These telescopes will be powerful enough to search for more than just the basic chemistry of life. They will search for techno-signatures, evidence of technology. This could be the unnatural heat signature of a planet-wide civilization, the glint of vast orbital structures, or an atmosphere polluted with artificial industrial gases like chlorofluorocarbons, chemicals that nature simply does not produce. The discovery of such a signal, faint and subtle though it may be, would be the most profound discovery ever made. It would confirm that we are not unique, that consciousness is not a fluke confined to this one small world, but is a recurring product of the cosmos itself. And the possibility that this confirmation might come from a world of two suns, a world we so recently condemned as uninhabitable, would be the ultimate testament to the universe's boundless ingenuity. Our perspective has been fundamentally irreversibly altered. We have been forced to abandon our cosmic parochialism, the comfortable but limiting belief that the universe must operate by the same rules that govern our own placid corner of the Milky Way. We have learned that stability can emerge from complexity, that harmony can be found in a gravitational duet, and that the conditions for life might be far more pluralistic, far more adaptable than we ever dared to believe. The universe, it seems, does not favour simplicity. It revels in diversity. It populates the cosmos with a staggering variety of stellar systems, from the quiet solitude of single stars to the intricate choreography of binary trinary, and even sextuple systems. Why then would we assume that life itself would be any less varied, any less creative? The search for life is no longer just a search for another Earth. It is a search for any world where the fundamental requirements, liquid water, a source of energy, and the raw chemical building blocks can be sustained. And we have seen with a clarity that would have been unimaginable a generation ago that these conditions can exist in the strange golden twilight of binary stars. This realization transforms our galaxy. It doubles, perhaps triples, the number of potential targets. It fills in the vast empty spaces in our maps of hope. The stars we once dismissed are now beacons of immense possibility. Every point of light in the night sky is once again a mystery, a question waiting to be asked. So the next time you find yourself under a clear dark sky, allow your eyes to drift towards the myriad stars scattered across the celestial tapestry. Know that more than half of what you see are not single points of light, but distant families of suns locked in an eternal gravitational embrace. And understand that around them, circling in orbits of breathtaking complexity, there may be worlds unlike anything we have ever conceived. Worlds with 2 dawns and 2 dusks. Worlds with skies of amber and rose. Worlds where the seasons are centuries long, and the tides are pulled by twin gravities. On one of those worlds at this very moment something may be stirring. Perhaps it is a simple, single-celled organism harnessing the light of its 2 suns. Perhaps it's a vast alien forest, its foliage tilted to catch the shifting rays. Or perhaps there is a creature standing on a windswept coast looking up at a sky that has never known the loneliness of a single star, and it too is asking the same question that has driven us on this journey. Are we alone? The answer is out there, waiting in the silence between the stars encoded in the faint light of those distant dancing suns. And for the first time in the history of our species, we finally have the tools, the knowledge and the courage to go and find it. Our journey is not over. It has only just begun.